Since this is our last meeting until fall, I was going to put underneath it to infinity and beyond, but that'd be plagiarism. So here we are. And because I only had a day to put this together because of a truncated vacation trip, I'm going to talk about T Coronae Borealis, which is a star in the constellation Coronae Borealis that looks to be going nova sometime soon. It's got a history of this. And that's going to be the whole bit, because I'm slow doing this. So here we are. T Coronae Borealis is a faint star. It's barely visible in binoculars. It's 2,700 light years away. Contrast, Betelgeuse is 600 light years away, and that's a supergiant in Orion. You can read this yourselves. It goes off periodically. And this quote, Dr. Schaefer is a professor at LSU. I read his paper. It's quite cool. Some predictions are it'll happen this summer, maybe next summer. But sometime in there, this thing is going to go off. So what is it? There. It's a binary system, two big massive stars. And the large Joule component is actually smaller, or was, than the one that is the hot white dwarf now. It aged more quickly, burned up its fuel, blew it off into space, and all that's left is the carbon-oxygen core, which is too small to go any further. It's quit producing energy, and it's extremely hot because it used to be the core of a star, and all the other stuff above it got blown off into space. And it's pulling material off its well-mannered red giant neighbor. When they turn into a red giant, when they start fusing hydrogen and making helium, and then that cooks off, so you've got two spheres of fusing material, and then stuff heavier starts fusing into the heavier elements inside. You can have 3 or more layers burning all at the same time. If it's big enough, they'll make iron. And within a day or two, it's all over because the iron can't fuse and it collapses. And that's a supernova. This isn't that big. It's blown off most of its outer atmosphere. Its companion is in the process of doing it. And a lot of that falls onto this white dwarf. And you think, okay, is it capturing hydrogen gas blown off its red giant companion? Yes, it is. And I saw some rather hokey looking animations of it, which are worse than useless in my opinion. What happens to the gas? Okay. This is a copy of a spreadsheet I built. The top line, it says G, 6.67 times 10 to the minus 11th. That's the gravitational constant. Universal. Okay, below that, we've got mass, radius, and acceleration. That is surface gravity. And on the far right, it's how many G's you experience at the surface. Now, it's kind of academic with something like the sun because it doesn't have a solid surface. However, if you look at the numbers for the sun, it's 2 times 10 to the 30th power kilograms. And its radius is about 700,000 kilometers. That's big. It's about 100 times bigger than the Earth, which is right underneath it, 6.44 times 10 to the 6th. But of course, the sun has much higher mass and much higher radius than the Earth. And its surface gravity, you can see in the third column in there, meters per second squared, 2.75 times 10 to the second power, 275 meters per second squared. Underneath is Earth, and that should be 9.81, but I rounded numbers off. So it's 28 times the gravity of Earth. Now the numbers for T Coronae Borealis, the white dwarf, it's got very close to, according to NASA, basically it's the mass of the sun. That's what's left behind. Used to be 10 or 20 times the mass of the sun. The stuff that's left is one solar mass in about the radius of the Earth. So dense doesn't quite describe this thing. If you look at the acceleration, and that's the bottom line, it's 3 million meters per second squared. So if you talk, well, in the previous talk, they were talking about how many G's do you pull launching in a rocket. And the space shuttle was good for about 5. On the surface of T Coronae Borealis, it's not 1 G or 5 G's, it's 328,000 G's. If you talk about pancakes, any life form there would be 1 molecule thick. A pancake, Bruce. So, when the gas gets sucked in to the gravitational well of T Coronae Borealis, it's not getting away. And it's compressed by its own weight in that gravitational field. And the star underneath it is 60,000 degrees Kelvin. So it's pretty hot. Now, this is what the light curve is doing. And this is from Schaefer's paper. It's kind of interesting. There's 2 different traces here. You can see the sinusoidal pattern to it. The stars take 228 days to go around each other. They're something like 1/3 of a light year apart. So they're moving. And that variation is just because they're going around to us and away from us and to us and away from us. But that magnitude on the left is pretty constant until you look at the lower right and you see that blue curve and the green one above it, and it's dropping. And the bottom is time in years. So it's gone about 5 months in 2023, and you can see that that light emission is dropping off. This thing is dimming. And they think it's because of the dust cloud, the gas and dust that's being blown off. It's getting thicker around this white dwarf. And this is what it did 80 years ago.
And then it went, whoa.
Well, the cool thing is, you think that's a pretty steep rise there, right around 1946 or so. Keep in mind that magnitude on the left, it's still, 10, 10 and a half, something like that. Then it dropped. And magnitude 10 is faint. I've got an 8-inch scope. I'm told I can pick up magnitude 14 stars. Not that I'd know, because I suck at star hopping anyway, but this is magnitude 10, and it goes straight up Well, magnitude 7, go another twice that distance, and you're up to magnitude 2. And that's what this thing ought to be doing, and it should happen in the next 12 months. In case you're wondering how the hell do I find that, where'd the cursor go? There it is. Okay. Here's your old standby, stellarium. And that was set to 11 o'clock tonight. And you can see on the bottom, you're looking at southeast to south. And you can see directly overhead at the zenith, that's 90 degrees. Arcturus to Vega. Everyone should be able to find Arcturus. Follow the arc of the dipper's handle, boom, there it is. And then you look to the east and you'll find Vega up there, nice and bright. Draw the straight line between them. It's there. Okay, zoom in a bit. This just sort of puts you in perspective. I have trouble actually trying to see that standing on the deck because I can't bend over backwards far enough to look 80 degrees straight up or I fall over. However, there's your straight line between Arcturus and Vega. Anybody who's been looking for M13 with a pair of binoculars, from Arcturus, a third of the way to Vega, where Lyra is, there's Coronae Borealis, and it's faint stars except for that one that's on the right. Yeah, okay, there's the cursor right there. That one's called Alphecca, and it's 2.2 magnitude, I think. This little circle down here, that's where T Coronae Borealis is. And when this thing goes off, it will be as bright as that star, which, you know, 8 magnitudes is pretty significant. And Hercules, M13 is either there or there, I forget which. And down there is the Ring Nebula for all the star hopping types. So this thing will last, probably, it will brighten in about 1 day. And it should be visible naked eye for 4, 5, 6 days. And what's happening is the layer of hydrogen that collects on the surface of this thing, as more hydrogen hits it, because remember, it's coming in under 300,000 Gs of acceleration. That's a lot of kinetic energy. And it heats it up, and eventually the hydrogen fuses. And you have an Earth-sized hydrogen bomb. And it goes boom, big time. So I'm really happy it's 2,600 light years away. And it should make for a pretty cool light show. And then if anyone here were 10 years old, you could tell your grandchildren in 80 years, oh, I remember when I saw it go off first. So here's the stuff on, yeah, it'll brighten in a day, be visible for several days, roughly the same as Alphecca. And this is the top left. If you go onto Stellarium and search TCRB, it's in there. I didn't put this in. It's in the database. And it's a variable star. That's the understatement of the year. Now, of course, this date and time thing, I just set it to 11 o'clock tonight so we know where things were in the sky. But this is going to be pretty cool, knowing you can watch a star go super, super bright. And one of the papers I was reading strongly suggested that not all of that hydrogen is going to disappear. Some of it will stay on the star. Meanwhile, the one that it's cannibalizing is blowing off hydrogen, helium, everything, because they do that. They expand, and it's that far out, the gravitational attraction is very weak, and it pulls it off of there. Its fate is probably to build up enough mass on this white dwarf that is there right now, that eventually it goes off in a type 1a supernova, which is lights out. I wish I knew more about the physics of supernova explosions, but being able to see this, and it bloops about every year, 80 years, they think. They've tracked it back to 1200. There's records of it, not every 80 years, but roughly. So this is the kind of thing that's going to happen roughly every 80 years, as far as people know. And maybe it's not as neat as, you know, a Hale-Bopp comet or something, but it appears to be more predictable. So there you have it. And when you see it, take lots of pictures and phone all your friends.